Students, now we are starting over new topic, that is the stationary waves in the stretched string. Before starting this topic, we will discuss about the laboratory experiment by which we can generate the stationary waves in the laboratory. For this purpose, we are using here the vibrator, and a string is fixed with the oscillator of this vibrator, which can oscillate vertically upwards and downwards. By which we can generate the waves of a particular frequency, and this frequency can be set through the vibrator, and it is a fixed end because this point Q is used as a fixed point because the string is passing through the pulley, and a hanging weight is used, or it is connected with the string to generate the tension in the string. Now when we start the vibrator and this oscillator will move vertically upwards and downwards, the waves are generated in this string, and after reflecting back from this fixed point Q, when waves come back towards the point P, now the interference will occur, and in the result of this interference the stationary waves will be formed. And all of these things we have discussed in the last lecture very precisely. Now directly I am drawing the profile of the stationary waves. For example, after starting the oscillator, this incident wave will move in the forward direction towards the point Q, and after reflecting from the point Q, the reflected wave will come back towards the point P, and in the result of interference between the incident wave and the reflected wave, the stationary waves is formed in this string. And we have two types of the points in this stationary wave, where these points where the amplitude is 0 and the energy level is 0, these points are called nodal points or nodal positions, and in simple we can say that these are the nodes, and on the fixed points the node will form, that is the point P and Q, and the points within the loops, and for example the middle point of the loop is called the antinode, where the energy is maximum and the amplitude is also maximum. Now to study the stationary waves in the stretched string, now we are using only the string part between the point P and Q. Now I am showing this portion from point P to Q in the separate diagram to study the stationary waves in a stretched string. Now I am drawing the new diagram. For example, it is one fixed point that is denoted by P, for example, and it is the string connected between the 2 points P and Q. Now I will generate the stationary waves in this stretched string. Okay. Now to generate this stationary waves in this stretched string, I will plug this string from different positions to generate the different number of loops with different frequency and speed and the different wavelengths. Now initially I am working for the n is equals to 1, where n is called the number of loops formed in the string, and it is a minimum number of loops generated in the string. And now we are considering here it is a point P and it is a point Q. Now I will plug this string from the middle position and at the time t is equals to 0, now the position of this string will be like this. It is plugged from the middle position, and when I release it, now the stationary waves will be formed and one loop can be seen in this string. For example, it is a one loop, and keep in your mind, students, on the fixed points always node will be formed, and because of the one loop the middle portion will be equals to the antinode, as we know already. And we are considering here the length of the string is equals to L, which can be denoted here, that is L, length of the string. And how many wavelengths are formed here? And students, we have already discussed that if we have the two loops formed in the string, for example, like this, from point A to B, it is a one wave. It is a one wave, and the distance covered by the one wave is called the wavelength. It means from this node to node, the alternate node position, the distance is called the wavelength. Now here we have only one loop, so this distance of one loop is equals to the half of the wavelength. So it means here we have the half of the wavelength formed. This distance is equals to half of the wavelength. Now we can describe the frequency. Before the frequency, we will discuss about the relation between length of the string and the wavelength generated for the one loop. So L is equals to lambda over 2, and the value of the lambda becomes now 2 times of the length of the string. Now we will find the frequency, and to calculate the frequency we will use here the wave equation, that is equals to V is equals to F lambda, and the frequency becomes now V divided by lambda, where V is the speed of the wave and lambda denotes the wavelength of the wave generated here. And we know that because of the one loop we have half of the wavelength. And now we will put up here the value of lambda in terms of length. So it becomes now the F1 is equals to V over 2L, because we are substituting here the value of the lambda from this box, that is equals to the 2L. Now this equation will be F1 is equals to V over 2L. This one shows the number of loops, because we have here n is equals to 1, and it is a minimum frequency generated here, because we cannot generate less than one loop in this string. So this frequency is called the fundamental frequency. And this fundamental frequency has another name, that is called the first harmonic. It is also called the first harmonic. Now we will generate the two number of loops in this string, and to generate the two number of loops